Welcome back to Differential Topology. I'm still Bryce and still talking about smooth things. And in particular, this time I'm going to be talking about the smooth maps that are in our category here of smooth manifolds. And just to be clear, what I've been doing up until now is defining the parts of a category. We've discussed the class of our objects, the class of smooth manifolds. But now, like any category, it has a class of objects and a class of morphisms between those objects. So just like when you studied topological spaces, you had the continuous maps between them. Now that we've got smooth manifolds, we need to study the smooth maps between them. So without drawing this out any further, let me address what it means for this map F between the smooth manifolds M and N to actually be smooth at a point P here in M. What it means is that there exists a pair of charts, one on M and one on N, such that P is an element of the domain of the chart on M, which is then a subset of the preimage of the chart on N under F. So I've got this pair of charts which obeys this nice preimage and containment relation. And then if the following map that I construct from it, this big composition here, is smooth at the image of P under XM, then I say that F is smooth. And before you get worried that you don't understand smoothness, and I'm using smoothness to define things down here, this is a function between Euclidean spaces. So you know exactly what it means for maps between Euclidean spaces to be smooth. You take their partial derivatives of all orders and ask if they're continuous. And if they are, then they're smooth. No weird abstraction required. It's a map it's a kind of function that you know how to deal with. So the smoothness of a function that we really don't know how to take derivatives of is defined in terms of those that we do. But notice that, so we define smoothness in terms of this local representation. But this local representation depends on our charts, X and M. It turns out, and this is what I'm going to show, among many other things, but this smoothness, while this local representation does depend on X and M, the smoothness of F at P doesn't. As long as we know that one of these guys exists, any chart pair that worked out for this would also have to satisfy this. And so I won't get ahead of myself too quickly, but we'll see for many reasons this definition is nice and manageable because it means you only have to find the existence of a pair of things, but it turns out to not necessarily just depend on those things exactly. So I'll get around to that for now, but for now, this is what I'll be meaning when I say a map is smooth. All right, so now that I gave you that definition which told me whether or not a map was smooth at a point or not, I'll say that a map F is called just smooth without having to say at the point afterwards if it's smooth at all points. So if I just say smooth, then I'm saying that at every point I could find a smooth local representation. But if I want to say that it could potentially be, not smooth in other places, I'd have to specifically say that it is a function that is smooth at that spot. So that's all. Now that I've got these two different definitions out of the way, smoothness at a point and then smoothness everywhere, we are totally ready to start getting on to some propositions. So first things first, I'm going to get to that justification that my definition of smoothness didn't necessarily depend on any particular pair of charts that obeyed that subset relation that I chose. So that will be coming up next. So right now I'd like to show, this isn't going to be very useful. It's just kind of a sanity check to show that defining smoothness in terms of some pair of charts doesn't necessarily mean that our smoothness depends on those pair of charts. So the way that we're going to show that is by showing that for any pair of charts, ym and yn, that obey the containment relation, this guy that we put in our containment relation for smoothness, then the local representation that I make with them is also going to be smooth, this time at a ymp. So let me show you why that's true. So let F be smooth at P by the definition that I just gave you, so that there exists some two charts for which the local representation is smooth at XMP, and I haven't written it here, but we know the subset containment relation is also satisfied. P is in the domain of my first chart, which is then a subset of the preimage of the domain of my second chart. All right, so that has to be the case because that's what it means for F to be smooth. So we have this pair of charts. Now let VMYM and VNYN be another pair of charts on our smooth manifolds, such that P is in the domain of my first chart, and that subset, or excuse me, that domain is a subset of the preimage of the domain of the second chart. So if this is true, then on the next panel, I'll show you that means we can actually get that the local representation in terms of these guys will also happen to be smooth. So let me show you that next. Now we've got pairs of charts that come from the same smooth structures on our manifolds. And so that means that these two chart transitions that I can make are smooth on their entire domains. And moreover, I know that the big long composition I'm about to make is defined. It is well defined as far as function composition, because this domain that I'm going to be restricting to in a moment is actually contained in the preimage of this domain over here. So that out of the way, that will just make sense for those of you who are about to eye with my composition here with suspicion. So this long composition here, which is this transition with my original function, which we know is smooth at XMP, and this transition function over here, eventually collapses down to give me a restriction of the local representation in terms of yn, ym to the open set intersect vm, which we know contains p. All right, that's all good, because that means that in here we have ymp, which is going to be sent all the way through till it becomes xmp here, which is going to be sent all the way through until it becomes yn compose f of p. But all of these maps all along the way, this map is smooth at xmp, which is all we need, and this map is smooth on its entire domain. So that means this final map here has to be smooth at ymp, which is great, because now we know that the local representation, this guy, the entire thing, not the restriction that I have here, this thing has to be smooth at ymp as well, because it has a restriction to an open set, which is smooth at that point. So, and it's a function on Euclidean spaces, so this is something that we already know about. So we know that this map here between Euclidean spaces is then smooth at that point. It has an open restriction that is smooth at that point, so that's all we need, and that means this is proved. So you only need to show for one appropriately chosen pair of charts that your local transition, I keep saying that your local representation is smooth at a point, but that is sufficient for showing that it is smooth for any choices of charts. So this definition, despite the fact that it doesn't reference all of the charts, it's just a matter of making it easy to use as a test. This proposition shows that it does indeed not depend on the transitions. It does indeed not depend on the representations chosen. So now that that's out of the way and I've proven that my definition makes sense, let's get on to something a bit more exciting. Okay, so now that I've justified my definition of smoothness for functions, I'd like to show that this definition of smoothness kind of has some of the properties that the smoothness of functions between Euclidean spaces had. For example, if a function is smooth at a point, then it should also be continuous at that point. That is a fact that's absolutely true in functions at Euclidean space, or in functions on Euclidean spaces. So let's see why that's true here. So if let's let f be some function that's smooth at p, so that we have some pair of charts that obey the containment relation that I keep writing down. P is in the domain of the first chart, which is a subset of the preimage of the domain of the second chart. And so that the local representation, this composition here, is smooth at the image of P. All right. So since this map here is actually a map between Euclidean spaces, and it's smooth at this point here, the image of P, it's also got to be continuous there. So let's just keep that in the back of our mind for a moment. Let V be an open set in the codomain smooth manifold N, such that the image of P under F is contained in V. Alrighty, we know that the image of P under F is also contained in U of N, U sub N rather, by that containment relation up there. So we know that their intersection is non-empty for one thing, and it must be a subset of both of the sets we use to make the intersection, just from set theory. And since it contains this image point, since the image point is contained in V and it's contained in UN, then this open set, V squiggle, V tilde, this is now an open set that I can send through Xn to make another open set, because Xn is a homeomorphism, so the image of an open set is an open set. So now, Xn, the image rather of V tilde under Xn, is now an open set that contains, I need to get my eraser out of the way, an open set that contains this point here, Xn compose F, P. So why is that important? Well, because that is exactly this point under this map, and this map is a continuous map at this point. Alrighty, so I'll write down exactly what all that means when I get to the next panel, but essentially that means that I'm going to get the open sets that I need to show that this function is locally continuous by sending the open sets that I get from knowing this one's continuous through these two homeomorphisms, because the image of something under a homeomorphism is also going to be open or closed depending on whether or not it was open or closed. So next panel, I will finish this up. So once again, having that our local representation was continuous at that image point, and that now Xn of V tilde rather is an open set that contains this image point, then it must be, since this guy's continuous, that there exists some U in Xm compose F inverse V tilde, that's the inverse of, that's this guy under the inverse of that guy, the pre-image rather, not the inverse, because I can't say that the inverse of that exists, but this fellow under the pre-image of that guy. So there exists some U in that set, such that XMP is contained in U, and U is open, because that's the definition of continuity at a point, and this guy between Euclidean spaces is continuous at that point. But that means that the image of U under XM inverse rather, is an open set, because XM inverse is a homeomorphism, so the image of an open set is an open set. And it will contain P, because XMP is contained in U. And moreover, the knowing, what do I need to know? Knowing this thing up here. This subset relation here gives me that the inverse image of U under X, or rather the image of X under XM inverse, it's the same here because this one is invertible, is a subset of the pre-image of V tilde, but the pre-image of V tilde is the pre-image of V because, is a subset of the pre-image of V because V tilde is a subset of V and pre-images preserve subset relations. So it turns out we have an open set here that contains P, which is a subset of the inverse of V, or not the inverse, gosh, I keep saying that, the pre-image of V under F. And V was just any open set that I chose earlier, which means that this is exactly F satisfying the pointwise definition for continuity. For any V open set that contains Fp, I can find some open set that contains P such that it is a subset of the preimage of V under F. So that means F must be continuous at P. And I'm not going to write it down, but there's a really quick corollary to this, which is that if you are smooth at every point, then you must also be continuous at every point. So if I say, smooth functions are continuous functions, where not specifying points after saying smooth and continuous is meant to say that they are smooth and continuous everywhere. So if you're smooth everywhere, then you are continuous everywhere, which is something that I will no doubt be using, because the continuity of functions is still very important in deciding a whole lot of these theorems coming up. Alrighty, so now that we've got this out of the way, we know that just like in Euclidean spaces, it's kind of natural. Things that are smooth are also continuous. Let's go see if some of the other things that happen in Euclidean space still work out, and we'll see some new stuff too. So we've seen that smooth maps between smooth manifolds are continuous in the same way that smooth maps between Euclidean spaces are also just naturally continuous. So now I'd like to show you that just as when we are in Euclidean spaces and we restrict a function to an open set in its domain, any point inside that new domain that our original function was smooth at, our new restriction function will also be smooth at. And this property carries over onto smooth manifolds and the maps between them as well. So let me show you that. So for any map F between two smooth manifolds, which is smooth at a point P, and any open set which contains P, the restriction F restricted to U is also going to be smooth at P. And let's see, it's fairly quick. So let P be some point inside of a set U inside of M where U is open, and let F be a function which is smooth at that point P. Then by the definition of smoothness, we know that that means there exists this pair of charts such that the containment relation that I keep citing is obeyed, and the local representation here is smooth at XMP. All right, so U contains P, and UM also contains P. So their intersection is a non-empty open set, and since XM is a homeomorphism, the image of that open set is also an open set. So this guy, this fellow, and not only is it an open set, it's an open set that contains XMP because both U and UM contain P, so their intersection contains P. So that means that this function here is actually a restriction of our original local representation, which is a map between Euclidean spaces, to an open set in its domain that contains the point XMP that it's smooth at. So this function, like I said earlier, is got to be smooth at XMP. But this function is actually equal to Xn composed with the restriction of F to U composed with the inverse of a new chart, the chart XM restricted to U intersect UM. So these two pair of charts are now a pair of charts in the respective smooth structures of my manifolds, such that this function has a local representation which is smooth at the image of P under this map that I'm inverting, which is the definition of smoothness. So F restricted to U is in fact smooth by our definition. So it's in fact true that restricting down to open sets that contain the points that we're smooth at retains smoothness. And a quick corollary to this is that if you were for example, you were smooth at every point in U, then the restriction to U has got to be a smooth map, because every point has got to still be smooth by our argument when we go down to the restriction. And so since there are the only points to talk about in the restriction, we say that map is smooth, and we don't need to refer to points anymore. So that's a quick corollary. It's not really worth writing down, but it's something that pops right out after this. So now that we've seen these two things, on with the show. Now, this theorem is going to be one coming to us from topology. Originally, it was just the pasting lemma, which was telling us that we could paste together continuous functions that overlapped properly in order to get another bigger continuous function. Here, we can in fact do that for smooth functions. So let me show you. So if we have some open cover of our smooth manifold, such that there is a set of smooth maps, which for every index alpha, the F alpha maps the open set U alpha into another smooth manifold N, and they're all going into the same smooth manifold, and for which any two indexes and any point that is in the intersection of two index open sets, I have that the functions with those two indexes, or indices, excuse me, agree at that point. So on all of the overlaps, all of these functions are equal to one another. Then there is a smooth map, F from M to N, such that this map, when restricted to any one of these sets in the open cover, is exactly equal to the corresponding function from the collection, from the indexed collection. All right, so to see that, first assume all the stuff that I gave as a hypothesis. And so we have an open cover of M and a collection of smooth maps that agree on their intersections. So if this is true, then I can make the following construction for a function. So if Q is in one of these open sets, then I want to make my new function f from M to N, and I will define it pointwise as f of Q is equal to f alpha at Q. Now every point Q is contained in some U alpha, so because this collection is an open cover, so it must be that this is a pointwise definition for every single point in M, because all you have to do in order to find out where Q is sent to, find out which of the open sets it's in. It could be in multiple, but it doesn't matter. You just take one. And then you define f at that point to be equal to f of whatever index contains your, whatever indexed open set contains your point, and the function corresponding to that evaluated at that point. And this is well defined because all of the functions that have that point in their domain are equal at that point by this hypothesis we've given of being equal on their intersections. So this is a well-defined pointwise construction for one of these functions, f from M to N. Now all that's necessary to show you is that it obeys what the claims that I made towards the end of my proposition, namely that the restrictions to any one of these open sets is in fact the corresponding function from the family from the index family, and that f from M to N is actually still a smooth map. So I've given you a map. Let's see that it's smooth and it restricts down properly. So I've defined f pointwise now. I've constructed it using my open cover and that family of smooth functions that I have. And from that definition, it really quickly follows that the restriction of my defined function on these U alpha is equal to my F alpha, because for every single point in U of alpha, F of my point is equal to F alpha of my point, meaning restricted to that open set is exactly equal to that function F alpha. So, and knowing that, and knowing that F alpha is in fact a smooth map, means that there has to exist two charts that we have here, such that P is in UM, which is actually contained in the domain of our chart F alpha, and obviously UM, the domain of our first chart, is contained in the preimage of the domain of our second chart. And then, once we have the containment relation, we then ask that the local representation, which is xn f of alpha, composed with xm inverse, we ask that this be smooth at xmp. But knowing that this f alpha is equal to the restriction, especially, and this is justified because we're still within our domain, UM here is going to stay within u alpha, so we're not going outside of this. So this function is equal to the restriction of our map F by our earlier work. And if we're never leaving this set, and also what by the definition of what it means to be a restriction, this has to coincide exactly with our function on that open set. So in fact, the function itself has two charts such that its local representation is smooth at every point P. Therefore, F has to be smooth at P, or F has to be smooth at every point P, so it is smooth. And therefore, and so having an open cover and a family of functions that agrees on the intersections and is smooth guarantees the existence of this larger global function. And this is one, but not the only way of creating a global function defined on an entire manifold. This is, frankly, the harder way. It's actually a lot to guarantee that all of these functions agree on their overlaps. But doing so absolutely does allow us to conclude that these things are smooth. We don't actually have to do that, though. Later, when we're a few episodes down the line, and I've introduced something known as a smooth partition of unity, subordinate to some cover, I'll be able to use families of functions on covers that do not agree on their overlaps, but still produce smooth functions from them. So that'll be something that is key. It'll be super important for creating, for defining integration properly, because, you know, we'll get around to it. But yeah, it'll be very important for lots of things. But so this is the hard way of globally defining a smooth function, asserting and proving that all of the family of functions agree on every single overlap. If you can do it, though, and you know it's certainly true, then this tells you that it'll work. If any of them disagree, however, you are going to have to be forced to use a smooth partition of unity, rather, which I'll be getting to in a couple of episodes again. So, but now that we know that we have the pasting lemma, so we can paste together a whole bunch of smooth maps to make another smooth map. Alrighty, now I have some quick propositions for you after this that don't really have a whole lot to say about them. So with those mid-length proofs out of the way, I'm going to deal with these rather quickly. Proposition 4 I'm going to deal with rather quickly because I'm actually going to let you deal with it. It's not all that complicated, and we don't really gain much insight by doing it. It's just kind of more of an exercise if you feel necessary, or if you believe me that the Cartesian product maps of smooth maps are smooth, then you can just go look up a proof proof on your own. You'll see it's not really all that complicated. Proposition 5, however, is going to be short because of some of the work we've already done. It actually follows immediately from Proposition 3 and the smooth pasting lemma, which is what I've written in a substitution of its proof, because if you look at the content of both the Proposition 3 and the smooth pasting lemma, you'll see it exactly deals with the forward and backward direction of this statement. So it really should be a corollary of that, but I've named it a new proposition, and it is that a map F between smooth manifolds is smooth if and only if, for every point, there's an open set such that the point is in that open set and the restriction to that open set is in fact a smooth map. So this is, it follows from the Proposition 3 because the restriction of smooth maps to open sets is again smooth, and it follows from the smooth pasting lemma because having a family of these smooth restrictions can allow us to extend up to a smooth map. So that's all fast. We can move on to something else, like some examples, which is what I'm going to do now. I'm going to start picking up some important maps that we can always define and showing that they are always smooth. So I'm going to start off with constant maps. All right, so back onto the train of things that we expected to happen between Euclidean smooth maps, still happening here between smooth maps between smooth manifolds. So constant maps are smooth, and what a constant map here is going to be is that for some point on a manifold, I'll define a function mapping some other manifold into that first one by f of p going to be equal to that point q for every single point p. So every single point in my manifold M is sent onto q in M. All right. Then for any chart that contains q in its domain, so any chart on N, it has to be that the inverse, or rather the pre-image of the domain of un, which contains q, the only thing in F's range, must be the entire domain M. So that means for any point P in M, and any chart on M that contains P in its domain, it has to be that the containment rate relation we use to generate the local representation is satisfied. That is, that the domain is contained in the preimage of the domain So this means we can construct our local representation. And it turns out our local representation, which is right here, for any point R in its domain, gives us the same point, because after sending R through xm inverse, I'll have to plug it into F, which will always give me Q, which will then always give me xn of Q. So this map is constant, and maps between Euclidean spaces that are constant are smooth. So every single point P for F here has a smooth local representation, which means it is in fact smooth by our definition of a smooth map. So just like in Euclidean spaces, constant maps are indeed smooth. We can expect that, adding, well, we might not be able to add, but composing or producting maps with constant maps doesn't necessarily affect smoothness, which will be very useful. So in order to form a category, I'm going to need that the identity map on any one of my objects is also a smooth map. But thankfully, just like it is in Euclidean spaces, or at least for maps in between Euclidean spaces, the identity map is indeed also smooth. And here's why. So recall that the identity map between on any smooth manifold, but really on any set, is just the map that takes in a point and gives it right back to you for any point in the domain. All right, well then if we've got this chart over here that contains P, then the domain of this chart is going to be contained in its preimage under the identity, because it is going to be equal to its own preimage under the identity. So that means we're justified in building our local representation, but by the identity rule, we can just drop the identity from this composition, and then by the inverse rule, we can create a new identity, and so now this is just the identity map between Euclidean spaces, which I said in the beginning was smooth. So because this guy is smooth at every single point in his domain, it has to be smooth at the image of P, and so for every single point P, the identity has a local representation which is smooth at the image point, meaning it is smooth by our definition, which is hopefully no great surprise. But it is one of the last pieces, not the last piece, but one of the last pieces that is going to show us that we are in fact forming a category here. All that's left now is for me to create my isomorphisms, which we will call diffeomorphisms here. And I also need to show that composing two smooth maps is also going to leave us with a smooth map. But I'll get to that soon. I still have a few more things to do now that I've got this. So let me show you that. Another very important example of a smooth map, or a set of maps that are smooth in general, are the projections, where a projection is a map from the Cartesian product of two sets that takes any ordered pair from that Cartesian product and maps it onto just the first coordinate in whatever the first element of the Cartesian product was. So it's taking from this larger space and projecting down onto this smaller space. So we call it a projection map. And to see why it's smooth here when these things are smooth manifolds, when these sets, here and here are smooth manifolds, let this be a chart on the smooth manifold m times n, which we know is a smooth manifold because it's one of the propositions from the smooth manifold, or from the submanifold and examples video. So we know we can make one of these charts such that it contains the ordered pair PQ in its domain. And then we know that because these charts that we get from the product structure are simply charts, the product of charts that are in the structure of M and N. So this chart must be in M structure. So we can use it because it turns out that PQ is inside of this thing, which we know, which is a subset of the domain of this chart cross the entire manifold N, because obviously N contains this thing, this set, and then this is equal to the preimage of the domain UM, because no matter what point in N you are, as long as you have a point in UM as your first coordinate, you'll land in there. So it's the entire thing that it's equal to. All right, so that means we can indeed form the local representation, And the local representation is now just going to be a projection between Euclidean spaces. And what's nice about a projection between Euclidean spaces, it's constant or independent of a set of variables and the identity with respect to another set of variables. So that means it is smooth because it can be differentiated with respect to all of its different variables, you know, all different partial derivatives of all orders, and they'll all be continuous. So this is in fact a smooth map for everything in its domain. So it's certainly going to be smooth at P, excuse me, at a P, comma Q. So that means that this map is in fact a smooth map. In fact, any projection map is a smooth map by this reasoning. And this will come back to us in not the next episode, but the episode after that, where we will be using something that requires this projection, or a projection rather, and we will need it to be smooth. So projections are smooth. All right, so this next proposition is going to be useful in the eventuality that I prove the Stokes-Cartan formula. I'll need to define several other things before we can actually do it, like, for example, manifolds with boundary. So far, the only manifolds we've discussed are ones that don't have any boundary. So the Stokes-Cartan formula would look a little simple to us right now. But after defining that, we'll also still need this theorem down here, which tells us that the inclusion map is smooth. And if you don't recall, an inclusion map is the restriction of the identity map to some subset of its domain. So it includes that subset in the bigger set. So in order to see it smooth, first I'm going to create a definition, an extension of this concept of being a function being smooth from having its domain have to be an open set to allowing it to be an arbitrary set in the following way. So a function f from some set x to n, where again x is an arbitrary subset of m, it's not necessarily open, maybe closed, maybe really weird looking. It's called smooth, that function, if there is an open set in M such that X is a subset of that open set, so that open set contains our domain, and there's a smooth map from that open set to N such that the restriction of this function to X, that set, is exactly our old function. So we have some smooth extension of F to the open set U. So that's what it's going to mean in order for a function on an arbitrary set to be smooth. And hopefully it isn't too hard for you to see that any function that was smooth before is still smooth under this definition of smoothness. It doesn't cause any other functions to become smooth that weren't smooth, as far as those functions that had open sets. So it totally still agrees with our previous definition of smoothness. It just extends it to a larger class of functions. All right, and so now we actually have what we need in order to show that inclusions are smooth. And it's actually not a whole lot of math because it's pretty simple. We showed that we showed that the identity map is smooth. So once we have this definition for what it means for a map on an arbitrary subset to be smooth, we know that any inclusion map is going to be a smooth map on a smooth manifold because it can always be extended to the entire identity on the entire manifold. That'll certainly be an open set containing any subset. And it will also be smooth because we already showed that. So every single inclusion map is smooth. Quick, easy, done. But it'll be important. We'll need to know this. So now that we've run through some examples of different smooth maps between smooth manifolds and even their subsets, I've decided that I'm going to hold off on the next series of smooth maps so that they have kind of a video all of their own. They're kind of special, they're important, and they're going to be the last little bits of information that wrap up why what we're talking about, the set of smooth manifolds and the set of smooth maps between them, in fact forms a category. So I hope you'll stick around with me for that. That will be coming up next time.